Okay, can everyone hear me out there?
Yes,
How about, can you see me too?
yes.
Okay, great, thanks. All right, so welcome back. This is our last week of class. And so we'll be reviewing the first 3 days. And let me mention, and I'll send an email out fairly soon about the details of the final. But I actually set up the final exam time on Zoom, and it's the same link as our class link. So let me say this up front. So the Zoom link for the final exam is the same as the class link. Yeah, I'll probably send that out also in the email because maybe some people haven't used the class link as much. So I'll try to do that. But I didn't want any confusion about having two different links. Okay. Okay, so that's the first point. And then the second point, I sent an email out this weekend, just as a reminder. So homework 12 is due tomorrow. Okay. And what I'll do is I'll take the top 10 homework assignments that you have. So we'll basically drop the lowest two homework scores. So it's easy if you just total your 10 highest, that'll be your homework total. All right. Any questions on this so far? All right. So what I plan to do for the review is I'm going to do the review in a reverse chronological order. So today I'm going to review the material which is from eigenvectors and eigenvalues on to the end of the class. And then I'll step backwards because you've had more of a time for review for the other material. So I thought we should actually focus on the last part of the course today. So if you have any questions, you'll have some time to ask me either today or tomorrow or Wednesday. Okay, so let's start. So the first topic is on eigenvalues and eigenvectors. All right, so the setup is as follows. So A is a square matrix, so it's an n by n matrix. So what we're interested in is we're interested in the following property. So we consider A times V is equal to lambda V, where V is not equal to 0. All right, so if this equation is satisfied, V is called an eigenvector. And lambda is an eigenvalue. All right. So as we've seen in the class, finding eigenvectors and eigenvalues are quite important because they allow you to actually change bases and write matrices in a simpler form, as long as you know how to actually conjugate the matrix from like a diagonal matrix to the original matrix again. And so so this is an important concept for computational purposes. All right, so the first thing is, how do you find eigenvalues? So as we've seen before, to compute eigenvalues, you have to look at the characteristic polynomial. So that's the determinant of A minus lambda I. All right, so this is a polynomial, which is an nth degree polynomial. So this is a polynomial in lambda of degree n. Okay, and the roots of the polynomial are the eigenvalues. Okay, so we've done lots of examples where we've actually found eigenvalues. Question? Okay, so once we actually find an eigenvalue or the set of eigenvalues, then we can find the eigenvectors. So given lambda an eigenvalue of A, we can consider, oops, oh, that did something weird here. Okay, let me erase that. Let me go back to the right pen and let me move it up a little bit. Oh, man, did it really go down there? Okay, so we have to keep on erasing somehow. Okay, we'll deal with it. Okay, so we should consider the eigenspace V lambda, which is basically the null space of A minus lambda I. Okay, and the non-zero vectors in the null space are the eigenvectors. All right. Okay. Any questions on this so far? All right. Now, what was this useful? Well, it was useful for the idea of diagonalization. So we know that A is going to be equal to P D P inverse if and only if, well, when we take the sum of the dimensions of the eigenspaces, I get n. All right, so it's easy to see when a matrix is diagonalizable. You just compute the dimensions of all the eigenspaces. If they all sum to n, then you know it's diagonalizable. All right, so this concept is saying that A is diagonalizable. Okay, so that's what this means. Okay, so it's easy to check. Once you have the eigenvalues, you can just check the dimensions of the eigenspaces. And then once you sum the dimensions, you can actually tell whether a matrix is diagonalizable or not. All right, so if I ask you a question on the exam, like, is this matrix diagonalizable? You can just compute the eigenspaces and compute their dimensions, and then you could say yes or no. All right.
Could you tell me the difference between dimension and rank real quick?
The dimension. So the rank is actually equal to, sorry, let me jack the volume up. Okay, so the rank is equal to the dimension of the column space of A. The dimension is just of a vector space or subspace is just the number of elements in a basis.
Okay, that makes sense. Thank you.
So let me write this down. So the dimension of W equals the number of elements in a basis for W. Okay? And we know how to find a basis for the null space. It's just a number of free variables. Okay, when you can actually solve the system of equations and you sort of write the solution out, and then you have your solution in terms of the free variables, and you take the vectors corresponding to the free variables, and that gives you a basis. Okay, any other questions? All right. Now, in this process, so if A is diagonalizable, then the D will consist of eigenvalues. So the lambda j's are the eigenvalues, and the P will be just an eigenvector corresponding to the eigenvalues above. So these consist of eigenvectors. All right, so I can ask you, for example, diagonalize the matrix and find the diagonal matrix and also the P, for example. Maybe I'll ask you to find P inverse too, who knows? But you know how to do that. Okay, any questions on this? Okay. All right, so let me give you an application. So an application of all this is to find like a to the 100th power. Okay, so this is not hard because if a is diagonalizable, then we saw that a to the 100th power is equal to p d to the 100th power p inverse. Okay, so once you actually find p and d, then you can actually solve this problem fairly easily. Because when you take d to the 100th power, you just take the eigenvalues to the 100th power on the diagonal. Okay, any questions on this? All right, so what was another application? Another application was the idea of difference equations. All right, so there are various difference equations that we saw. The first one we dealt with was the one involving the Fibonacci sequence. Okay. Another example of a difference equation that we saw was with economic systems. And then finally, we actually dealt with predator-prey models. Okay. So, so basically, they all are kind of the same, right? So you just have something like x to the k is equal to like a to the k. Sorry, that's not right. Okay, so you have something like this, like x to the k is equal to a times k minus 1. Or maybe this is a k plus 1 here. Okay, so maybe it's like this. Okay, so that's probably better. All right, so basically the idea is that the next step is given by applying a to a vector. And then you have an initial value condition. So x0 is the initial value. Okay. Now, let's just look at this for a second. So if I want to know what x1 is, that's going to be a to the x0, right? If I want to know what x2 is, well, that's going to be equal to a times x1, which is equal to a times x0. So that's a squared x0. So in general, a to the k you obtain by just iterating by a to the k x 0. All right. So if you know what a to the k is, you can actually find what x to the k is. So if a is diagonalizable, then we know that a is going to be equal to PD P inverse, and x to the k is going to be equal to P d to the k P inverse times x 0. Okay? So you can actually solve for this by doing this. Now, if you actually want to write things out, there's an alternative way to do this. So alternatively, there's another formula that we derived. So x to the k is equal to C1 lambda 1 to the k V1 plus C2 lambda 2 to the k V2 plus Cn lambda n to the k Vn. Okay, so the V's are the eigenvalues, or vectors, sorry. So this is just another way of writing it. Okay, and x0 is equal to P times C1 up to Cn. Or in other words, C1 up to Cn is the inverse on x0. Okay, I mean, it's the same thing as what I wrote in the box, basically. All right, so you should definitely go over an example or two of predator prey. I think you have one from your homework. We actually went through several in class, so you should know how to work with those. Okay, any questions on this so far? All right, so let's move on. So the second topic I want to talk about today is the topic of orthogonality. All right, so we defined orthogonality using the dot product. So we have U dot V, and the way we defined it is by matrix multiplying U transpose times V. So U is a vector, which is looking like a row here. And then we have a column. And so what do we get? We get U1 V1, U2 V2, plus UN VN. All right. Now, what else do we know? Well, the reason why we did this was we had this inner product formula. So we had that the dot product was what? The absolute value of U, V, cosine of the angle between the two, where the length is given by the square root of the sum of the coefficients squared. Okay, so a main point is that U and V are orthogonal if and only if the dot product is equal to 0. Okay, so the cosine of the angle between the vectors is like 90 degrees. All right, so so this is called the length. And notice that if I take the dot product of U with itself, I get the length squared. All right. Okay, so we also had this notion of orthogonality of sets. So a set U1 up to UN, maybe I should say UT, is, well, there are two definitions. So there's orthogonal, if and only if ui.uj is 0 for I not equal to j. So pairwise, each of the vectors is orthogonal to the other vector. Okay. And it's orthonormal if, well, you have the orthogonality still, and you also have that the length of each vector is 1. Okay, so any orthonormal set is orthogonal, but not every orthogonal set is orthonormal. You need that the lengths of each vector is 1. And so if you want to transform an orthogonal set to an orthonormal set, you can just divide by the lengths of the vectors, and that'll produce an orthonormal set. Okay, any questions on this so far? All right, so here's kind of a study guide. So know how to do the following. 1, you should be able to know how to determine if a set of vectors is orthogonal or orthonormal. Yeah, I could just hand you a set of vectors. You should be able to tell me whether the answer is yes or no and why. Okay. So 2, given an orthogonal set, how to make this into an orthonormal set. All right, so I mentioned this before, if you have an orthogonal set, then you can make it into an orthonormal set by just dividing by the lengths of each vector. Okay, it doesn't change the orthogonality by doing that. All right, now U is an orthogonal matrix if and only if, when I take the transpose times U, I get the identity matrix. Okay, and this is the same thing as saying that the columns of U are orthonormal. Okay, any questions on this so far? All right. Now, the good thing is orthogonal and orthonormal bases have very nice properties because you don't have to use Gaussian elimination to find out how to write one vector in terms of the basis. What you can do is you can just use inner products instead to find the coefficients. All right, so this is quite useful in the idea of orthogonal projections. So, all right, so here's the idea. So let U1, U2 up to UT be an orthogonal basis for W. Okay, so W is a subspace of Rn. Okay, so you take a subspace and then you want to look at an orthogonal basis. All right, so given a Y in Rn, I can actually write Y in terms of a vector inside a W and then something orthogonal to the subspace W. So Y is going to be equal to Y hat plus Z, where y hat is in W and Z is perpendicular or orthogonal to W. Okay, so that's the same thing as being in the orthogonal complement. Right? All right, so the picture looks something like this. So here's your subspace W, here's your Y over here, and the theorem says I can actually project down onto here, and then here's the Z. So I can decompose Y in terms of something in W and then something which is perpendicular to W. And the nice thing is when you have an orthogonal basis, the formula is rather explicit. So Y hat, which is the same as the projection of Y onto W, is given by the following formula. Y times U1, U1 dot U1 times U1, Y dot U2, U2 dot U2 of U2, and then Y dot UT, UT, UT times UT. Okay, I'll just emphasize that these are vectors there. Okay, any questions on this? And the idea of orthogonal projection. So, one problem is, and I mean, we did a lot of this in homework, is that I can give you a vector in Rn, I can give you an orthogonal basis. I can ask you to decompose Y in terms of something in the span of that orthogonal basis and something perpendicular to that subspace given by the span. All right, questions on this process? Okay, good. All right, so the next thing I want to go over is the Gram-Schmidt orthogonalization. All right, so what was the idea of Gram-Schmidt? So the idea is that I can actually kind of reverse engineer this process. And so suppose that I want to actually straighten a basis out. So imagine that Y and Y hat are sort of in a subspace. Then I could sort of straighten this basis out by taking the Z, right? So that's the idea, is that we can use projections to actually straighten a basis out to make it an orthogonal basis. So given, I'll call them x's, call x1 up to xt, basis for a subspace W, let's say in Rn, one can find an orthogonal basis V1 up to Vt of W. Okay, and I can give you a recipe for actually doing this, right? Okay, so the first thing you do is you set V1 to be equal to the first vector, and then V2 to be equal to x2 minus x2 V1, V1, V1 on V1, and so forth and so on. So x3, and then you just subtract off the projection basically. So x3 V1, V1, V1 on V1 minus x3 V2, V2, V2 on V2. Okay. And then you just, continue this process on. So you get Vt to be equal to xt minus xt V1, V1, V1 on V1 dot 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 minus xt vt minus 1 vt minus 1 vt minus 1 and then vt minus 1. Okay, so just want to emphasize those are all vectors here. Okay, any questions on this? We've done lots of examples of this too. So if I give you a basis for a subspace, again, you should be able to find an orthogonal basis for the subspace by just using the Gram-Schmidt orthogonalization process. Okay, just plug and chug. That's all it is. Just make sure you don't make mistakes. Okay? It's very easy to do. All right. Let me also mention that you should also know how to do the QR factorization. I think you had some in your homework problems. So I'll just say this, review how to do the QR factorization. So basically, to do this, you just take the columns of A. That's the basis for the column space of A. You just straighten it out by using the Gram-Schmidt process, and then you put the V1 up to VT in the columns for Q. So then what you do is you just take the transpose on both sides, and then you're good to go. So actually you have to divide by the lengths too. So maybe I should just go over this. So, so the process is take columns of A, okay? And I'm assuming that, I guess that A has linearly independent columns. So we better make sure they're linearly independent. Otherwise, it's not a basis for the column space. And then, so we're assuming at the beginning they're linearly independent. And then what you do is you apply Gram-Schmidt. Okay, of A. So we get V1 up to Vn. And then you want to also normalize to get an orthonormal basis. Okay, so you want to divide by the lengths also. Okay. So we'll just say V1 up to Vn still, right? All right, then what you do is you set Q to be equal to the columns of these vectors. Okay. And then if I want to find the R, then I just multiply by the transpose. So QT transpose A is QTQ times R. And because your columns are orthonormal, Q transpose Q is just the identity. It's an orthogonal matrix. So that gives you R, okay? So in the process, R is just going to be Q transpose A. Okay, like I said, this is open note test, so you'll have this available. So you don't have to totally memorize this, but you should sort of understand how things work. All right, questions on any of this so far? Okay, so the last thing I want to talk about today is the notion of least squares. Okay, so let's see, that's going to be, I guess, number 3 here. Okay, so number 3 is the idea of least squares. All right, so let's briefly run over the idea of least squares. So I have AX equals B, where A is an m by n matrix. Okay. And this may be consistent, may have a solution, it may not have a solution. But if it doesn't have a solution, what we want to do is we want to actually find the best possible solution. So here's a picture over here. So this is the column space of A. Okay, so these are all values, possible values of A times X. Okay, so all solutions of this in some sense. But the B might not lie inside the column space, right? The B might sort of live out here. So what we want to do is we want to find AX, which is closest to B. So we want to find A times X that is closest to the vector B. That is, we want to minimize the error between AX and B. Okay. And what least squares, so the reason why it's called least squares is because, the length is given by the square root of, the component squared, right? So you're basically minimizing the distance function. All right, so one thing we learned in this least squares process is that if we do have a minimal solution, it has to satisfy the following equation. Okay, so a solution to the least squares problem satisfies the following equation. A transpose A times X is equal to A transpose B. Okay, this was the minimum, or actually, I shouldn't say minimum, but it was the equation that has to be satisfied if you want to actually have a solution which minimizes the distance. Okay, so this is all we can say. There could be, like, we had an example where there are many least square solutions. It's not necessarily unique. When it is unique is when A transpose A is invertible. And what condition would actually guarantee that A transpose A is invertible? Anyone?
The columns are linearly independent.
Good. All right, so that's what we learned. So if A has linearly independent columns, then we can guarantee that A transpose A is invertible. So if A has linearly independent columns, then A transpose A is invertible. And then you get that X is going to be equal to A transpose A inverse A transpose B. Okay. And if you want to look at the projection, the closest point, I have to apply A again. And the closest point, AX, is going to be equal to, well, it looks very similar to the projection, but with matrices instead. Okay, so this is a projection matrix here. And you just take that projection matrix and you apply it to B, and that's what you get. Okay, so know how to find least squares solutions. Okay, you should definitely know how to do that. All right, now we can also do this for data fitting too. All right. I don't know, I probably won't give you anything worse than a linear one. You should still be able to do other ones, but the linear one is what I want you to be accountable for, okay? So another application of this is, I'll say it's linear data fitting. All right. So given points, let's say they're y1, t1 up to y, let's say, what did I use? I used m, right? I think I used m in my other notes, tm. So given m points, all right, so again, this looks something like this. Here's the t-axis, here's the y-axis. You know, you have a bunch of points like this all over the place. The idea is you want to actually fit a line or find a line which actually best fits the data. So you're going to find a line here. Okay, so let's say this line has the form y is equal to c plus dt. Okay. Now, so in order to find the least square solution, you have the following. So you have ax is equal to b. Here, your x here is going to be equal to c and d. And let me just write all this out. So here's your c and d. And your b is going to be equal to y1, y2, up to y sub m. And then you have 1 t1, 1 t2, 1 tm. Okay, so this is your a, this is your x, and this is your b. All right, so you know, I gave you an actual formula for computing x out, but you know, if you want, you know, you could just start with this and then just use the previous formulas up here. You know, you don't have to memorize it. You can just kind of rederive it if you want. Okay, so I actually gave you some formulas in your notes, which you certainly could use, but you know, you can actually rederive it by just starting out with this and then just applying least squares to that. Okay, it's not maybe easier just to start off with ax equals b and just apply least squares. Okay, so then you want to apply the least squares method. To find the coefficients which will give you the line. Okay, so you know, you should be able to do for the last part of the course. You know, I understand that the course is kind of compressed at the end. You should definitely know how to do you know, homework type problems. I always ask you to be able to do homework type problems, but some of the things that are fairly standard types of problems: finding least squares, you know, to diagonalize a matrix, you know, finding solutions of difference equations, you know, finding whether, you know, vectors are orthogonal or not, you know, working with orthogonal projections. I mean, these are all sort of the standard types of problems. Okay, so I have a few minutes, so let me open it up to any questions that you may have on this material. No questions? You can always, let me say this: if you have if you're not quite sure about something and you want to kind of look it up and think about it overnight, you can ask the question tomorrow too. Okay, so if you you know you wake up in your sleep tonight and you have this burning question that you have to ask me, you can just ask tomorrow at the beginning of class on this material. Okay. All right. So tomorrow we'll actually probably go over some of the middle part of the course. And then, if we have time, we'll sort of touch on the first part of the course. But by now I'm hoping the first part of the course is pretty solid in some sense. Okay, last call for questions.
One question just about the
Sure.
exam. So on Wednesday, are we gonna go over like maybe any definitions we may need to know for the exam, or is that just
Yeah. So what I'll do is, well, one good thing is it's open book, right?
Yeah, that's true. That's right. That's right.
That'll definitely help you out. Yeah, I don't know if I would definitely, open book tests are a little bit different. I mean, I don't want you to just have to regurgitate something and copy out of the book.
Okay.
So, it'll be a little bit different than a test which is not open book, a closed book test.
Gotcha.
But I don't want to make it like way harder or anything. All right. So it might be slightly more open-ended. I mean, I may give you a problem where you have to actually, think about something and write something down, which may not have like, a unique answer, for example. I don't know if that makes sense, but so there might be a little bit more open-ended questions. Okay, other questions? Okay, like I said, I mean, if you haven't, I'll try to leave a little time at the beginning of next class. If you guys have any questions about concepts or anything like that, we can do it at the beginning of next class and also at the end of next class. And I'll try to have some part being a sort of more or less set review. Okay. All right, so if there are no other questions, we will see you tomorrow at the same time. All right, have a good day.
Thank you.
All right,
Thank you.
welcome. Mhm.